We all use receptacles every day to power our electronic devices, but how do these work? Hey there guys, Paul here from theengineeringmindset.com. In this video, we're going to be looking at how receptacles work, the different parts, how they're wired, as well as the purpose of the ground wire. Now we're going to be using the color coding and terminology for North America in this video. But if you're from outside this region, you can still follow along and learn how they work, or you can check out our other videos. Now we are just covering the theory in this video, but remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. So if we take a typical receptacle, we're going to find two neutral terminals on the left which are silver in color. And then there will be two brass colored hot terminals on the right. We'll also find a green ground terminal also. Between these respective sets of terminals, we have a jumper, but we're going to come back a little later in this video and look at that. Inside the outlet, we'll find some tracks which will carry the electricity. The two neutral and the two hot terminals are currently joined together by the jumper. So both hot terminals will become energized if either one of the two were wired into the circuit. We can remove the jumpers by using some pliers to just snap them off, but these can't be replaced. By snapping these off, we can isolate the terminals and connect them to different circuits. We'll look at this in detail a little later in this video. For now, I'm going to leave these jumpers in place. We can connect this receptacle into the electrical system by first bringing in our hot wire and connecting that to the hot terminal. Then we bring the neutral wire in and connect this to the neutral terminal on the opposite side. To make the circuit safe, we bring in our ground wire also. If we now turn on the power, the electricity will flow along the hot wire and into both the tracks for the hot terminals. The electricity wants to reach the neutral terminals to return back to the service panel, but it can't at the moment because there is no path to complete the circuit. As I said, with the jumper in place, both hot terminals are now hot. But if we remove the jumper between these two, then only the terminal connected to the hot wire will be energized. In this case, that's the top outlet. Coming back, to complete the circuit, we need to plug something into the receptacle. For this example, I'm just going to plug in a simple light fitting. With the light plugged in, the electricity can now flow through the hot terminal and into the plug. It will then flow along the cable and into the lamp. From there, it will return to the neutral terminal of the outlet and then return to the service panel and off to the transformer outside the property, where it will complete its circuit. With the jumper in place, the lamp will also light up if we were to plug it into the lower socket. But when we remove the jumper, the circuit is broken and the lower hot terminal, in this example, is no longer hot and will not power the lamp. With the jumper still removed, we can still plug the lamp into the top circuit to complete the circuit and power the lamp. So then, why would we want to remove the jumper? One application is when using switch receptacles like this circuit here, which allows half of the receptacle to remain hot while the other half is controlled by a switch. For this, we bring the hot wire in and connect this to the wire nut. We then run another hot wire from there and over to the top hot terminal. We can then run our neutral wire back to the service panel. Of course, we need to also include our ground wires too. If we powered this circuit, then only the top half of the circuit would be hot. The lower half would have no power. So to connect the lower half to the switch, we run a white wire from the hot wire nut and take this over to the lower terminal of the switch. We then need to place some tape on this wire to warn that it is hot. Then, from the top terminal of the switch, we run a black wire over to the lower terminal of the receptacle. To make the circuit safe, we bring in our ground wire also. Now when we power this circuit, we again get electricity to the top terminal, and we have given it a second path which leads over to the switch. The switch is off currently, so electricity can't pass it. But when we flip the switch, the circuit is now made and electricity can flow over to the lower half also. If something was plugged into either of the sockets, then electricity can flow through and into the neutral side to get back to the service panel. If we flip the switch off, then the power is cut again to the lower half, but the top half will remain hot. Another application is to connect to two different hot wires. If we remove the jumper and then bring in a red hot wire as well as the black hot wire, we can connect the top half and bottom half to different circuit breakers. This will spread the electrical demand over two breakers instead of just one, so it's less likely to overload and trip the breaker. So far I've animated the flow of electricity using DC or direct current which flows in one direction, like the water flowing down a river. I've used this method because it's simple to visualize and understand. But electricity in your home flows forwards and backwards because it's AC or alternating current. It flows like the tide of the sea, back and forth constantly. But don't worry too much about this for now. If you want to learn how electricity works, then check out our simplified tutorial on that, links down below. Additionally, we've also covered split phase electricity in great detail. Do check this out, links down below. The next thing I want to briefly cover is the purpose of the ground wire in the circuit. This wire is an emergency path to try and save you from an electric shock. Ideally, the ground wire in the circuit will never be used, but should a ground fault occur, then the wire is on standby, ready to take over. Under normal operating conditions, the electricity will flow into your home through the service panel and circuit breaker and then into the hot terminal of the receptacle. If we plug something in, then it could make its way over to the neutral wire and then out through the neutral incomer and over into the transformer outside the property. Again, I'm just animating the flow of electrons in one direction for simplicity. In the event of a ground fault, which is where the electricity took an unexpected route back to the source instead of passing through an electrical device, for example the hot wire came into direct contact with a metal casing, then the electricity will flow through the metal body and into the connected ground wire, where it will continue over and then either pass through the neutral or a separated ground busbar and then up through the neutral wire and over to the transformer. As this occurs, the current in the circuit is going to increase dramatically and almost instantly. In most cases, the sudden and large rise in current is detected by the circuit breaker, which will trip to cut the power to the individual circuit. The electricity will continue to flow into the building and into the other circuits on the service panel. The fault will then need to be corrected and the circuit breaker flipped again. We've covered ground, hot and neutral wires and faults in great detail in our previous tutorial, links down below for that. Okay guys, that's it for this video, but to continue your learning then check out one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram as well as theengineeringmindset.com.